lines of regression. Least squares lines of regression. I think it was chapter 3 or 4 that we talked about these. And we're going to expand on it. I think there's a great reason why the book put this at the end, especially for those of you that are taking the AP test. Hey, those of you that are taking the AP test, least squares line is going to be fairly heavy on it. I would almost bet. So you're going to have to be kind of brushed up on this. So least squares line of regression. I'm going to make a really quick review on that because it's been a long time since we've looked at it. So what is a least squares line of regression? It's just really a line of best fit, right? Or just a line of regression. So if we have some data, it's the line, and it may not touch any of the points, but it's the line that's the best average of all the points. And the reason they call it least squares is they use the distance that a point is from a line. It's the least amount of distance to a line for all of the box. It ends up being a box that the computer calculates. So needing to be able to calculate it is not something you need to know. Just if you see least squares or just line of regression, know that it's the same thing. Okay? And really it's a line of best fit. Now, r and r squared are a couple of the things that we get from that calculation. If you're planning on using one of my calculators for the test, and I should have plenty, I'll probably have to borrow some from other teachers, which is totally fine. But you will not get an r squared and r value if your mode is not correct. So you might double check. If the stat diagnostics is off, you're going to be going like, why isn't this calculator telling me r and r squared? You got to have your stat diagnostics on. It's probably not an issue if you have your own calculator, but if you're using mine, sometimes people reset them and that gets shut off. I don't know why it's not default on, but it's a default off for some reason. So remember, r is how scattered the data is. It sounds like the Who's are singing next door. How scattered the data is. And remember, that has a limit from -1 to 1. Where -1 is a line that's trending downward, and the points pretty much all fall on the line. A +1 would be it's trending upward. It doesn't reflect the actual slope, it's just that it's going up. And the points would be very close to the line. Anything between that is some amount of scatter. Riley, you with me? Yeah. Okay. A 0 would be no correlation at all. The data is scattered all over, and there's just nothing there for us. What's the r squared then? Anybody remember what r squared is and how it's different than r? Other than it's just r squared. Yeah.
Strength of your prediction, right?
Exactly. It's the strength of prediction. Yep. In fact, I'm going to use exactly those words. The prediction is going to be your y hat value. And this is anywhere from 0 to 1. Since it's squared, it can't carry a negative value. Where 0 would be, there is no, your prediction's total junk, to 1, 100% of the time, you're going to get a good prediction. So somewhere in between there Like if you had 0.75 for an r squared, that would indicate that about 75% of the time you expect your prediction to be good. All right. All right. So these are two ways also to decide if the data is linear. Does anybody remember what our values are for that? If r is greater than positive or negative 0.7, so I'm going to say the absolute value. Hang on. How do I want to phrase that? The absolute value of r is greater than 0.7? Or should I put the absolute value around the 0.7? I'll do that. It's the end of the year. My math brain is totally toast. R has to be greater than 0.7, positive or negative. Okay. And when I say negative, right, negative 0.8 is greater than negative 0.7 in this example. R squared has to be greater than or equal to, anybody remember? 0.5, yeah, good, 0.5. So if these are true, then we say that there's evidence of it being linear. The book will say that it's linear, but there's really a third thing to look at. And here's the deal. If this is true, then that's true. If this is true, then that's true. So you don't really have to check both. It's just if one or the other is true, you can say your stuff is linear. But the real thing is the residual plot. The residual plot is where we really, I think, this is the best way of saying if something's linear. Residual plot would be one of those deals, remember, where we make the calculation and then the computer stores the residual values and then we graph it. We always get a horizontal line. And then what we're looking for is a scattering. Strangely enough, if it's scattered in the residual, that's an indication that it's linear, right? So scatter. If yes, then it's linear. If no, meaning there's a pattern, not linear. So we're actually looking to see if there's a pattern. So an example might be if you look at this and you see something like this, where there's some pattern or another, here it's parabolic, then that would be an indication that your data is not linear. Here's why this is a little bit stronger than just one of these. Everybody with me? If you don't have to copy this down if you don't want, but if I graph some data, let's say I have some data and it's all over here. It's in a small band. And I get an R value, let's say R equals, I don't know, 0.83. Okay, it's positive and it's 0.83, it's strong. We go, oh, that's linear. But then we graph the residual plot and it shows a pattern. Why might that be? Well, here's the reality. If I have data that fits on a curve, if you cut a small enough piece out of that curve, what does that small piece look like? It looks like a line, right? So on a very small section of a possible curve, it could look very linear. In fact, it might have very good when in reality, the actual situation is a curve, and that's where the residual plot helps us out to identify that. Cool? So residual plots, pretty good idea too. Check that.